Hello, welcome to this tutorial where I would like to introduce you into the development system for disturbance emission testing, which is called ESA1 system from the Langer EMV Technik. The system is very good if you have no big anechoic chamber or shielding room for emission testing. So the system comes with such a small shielding box here and with some other equipment where you can do some emission testing or some troubleshooting on your working desk. This is a very small setup and very easy to use. And this is what I would like to introduce you. And let's start with the complete setup of the system. At first, I would like to show you which components are included in the ESA1 system. Here we have the metal ground plane, what we need as a reference plane for all of our measurements. Then we have here the shielding tent and the frame for the shielding tent. The other components, what you can see here on the left side, are from the small box. We have here the RF current transformer. This is our main part for our measurements, what we have to use for all of our measurements. We have here a RF bypass, which is where some capacitors or capacitance is included here in this small box, and we can use it to create a capacitive load for our electronic components. Then you can see here the preamplifier. This preamplifier works in a frequency range from 100 kHz to 3 GHz. For this preamplifier we have here a power supply and a small power supply connection cable to connect it inside the tent. Then we have here some other cables. We have here some small cables to connect our electronic, our tested electronic. We have here RF cables. One RF cable is here with a SMB connector, and on the other side you have the BNC connectors. And the second RF cable, which comes here with the two BNC connectors. These two cables here are for the DC, for the power supply connection, for the DC power supply connection. Then we have here a USB drive with our software, with our ChipScan software, to monitor and to show all the measurements on your computer. And a USB dongle, what you need for the connection of external devices. Then we have here some other clips, some micro clips here. We have crocodile clamps and other connectors what we need to create a connection between our measuring devices and our tested electronic. And the last one are what you can see here are a lot of near field probes, different types of near field probes. We have electric field probes, we have magnetic field probes. These probes you can use these probes in a frequency range from several megahertz up to 3 gigahertz. And you see here that we have different sizes of the probes and different probe tips for the different measuring tasks, what you need to analyze your electronic and for the troubleshooting and to find the emission, the source of the emission on the electronic. Before we can start with our measurements, we have to set up our shielding tent. Here we need our reference plane, this ground plane, this basic ground plane. And in this ground plane, what you can see here, we have different connections to the outside. We have, for example, RF connectors. Here you can see with the SMA connections to put to the outside or also to the inside some RF signals. Then we have DC connectors, filtered DC connectors to put some power supply into the shielding tent. Here we have another SMA connections. Then we have here a BNC connectors or BNC connector. What we normally use here to connect the preamplifier to the reference plane and to put the measured signals to the outside. Then we have here the small power supply for the preamplifier. We have a USB connection, inside USB-A, and the outside we have USB-B connector. Then we have here the RJ45 connector for Ethernet or something else. And we have here an AC connection if you want to do some measurements with devices which are powered over an AC power supply. Now the next step would be to put the frame here on the ground plane. For that you have to plug in the frame very easily here over the two dots into the ground plane, and then you can see here it is also possible to open this frame or the complete tent here to have a better access to your electronic device, and you can also close it again. Now we have to put the shielding tent over the frame, and to get a good connection between the shielding tent or material and the reference plane, we have here in the side of the tent some magnetic stripes. And you can see here it is very easy to get the connection to the reference plane. On the top side of the frame or of the shielding tent you have two fasteners, and you have to close these. Now you are ready to use this shielding tent by closing it to have a complete shielded room. Now I want to show you the installation of the main components inside the shielded tent. What you can see here, so we will start with the power supply cable, with this short cable here for our preamplifier. And for this cable, for the short cable, you have here the 12-volt power supply socket. You can plug it in here. Then we have to install the preamplifier here with the ESA1 set. There is 20 dB preamplifier. This is called PA203. This is or the frequency range of this preamplifier goes from 100 kilohertz up to 3 gigahertz. So it's definitely enough here for all of these measurements what you want to do inside these test box. So this preamplifier has a BNC connector, and that's the reason why we use also the BNC connector here in our reference plane to connect it or to connect it to the preamplifier. And of course this short power supply cable you have to plug in here to the preamplifier. So the next step will be our main measuring equipment, main measuring box here. This is the RF current transformer, and with this current transformer you can measure the emission of the complete device. So normally in the setup here, what I would like to show you. This is for, let's say, 80% of the applications of the measuring tasks. When you have an application with a DC power supply. And for this, you have to bring these RF current transformer box here into the power supply of the device under test. You can see here that the RF current transformer has a metallic bottom side, and with this metallic bottom side you have to place it directly onto the ground plane. Inside this box here you can see that the power lines or the supply lines here have a capacitance to the reference plane. This is a very low impedance capacitance, and the reason for that is we need this capacitance here that all of the disturbance of the emissions which is created by the device under test. The device under test you have to connect here on the right side of the RF current transformer, so that all of the disturbance which is created by the device under test, that these disturbances are coupled to the reference plane, for example, and then the disturbance has to go back to the source of the emission, which is normally the electronic itself. And here we provide as a return path, we provide this low impedance current path over our RF current transformer, so that the current goes back this way over the power supply to the electronic itself. And here inside the box we have now the possibility to measure exactly these disturbance currents which are created by the electronic itself. And then you have here the RF output where you can put out, or where the measured signal is put out. So then you have also, for conducted measurements, you have two possibilities here. One possibility is to measure the common mode disturbance current, and on the other side here, the second connector, is to measure differential currents. Later I will explain why this is sometimes important to measure common mode or differential mode. Now we need these short DC power supply cables here to connect it on one side to the RF current transformer, and then you can choose one of these DC power supplies here in the ground plane to power your device. And now I need this RF cable here with the SMB connector. One side I connect to the RF current transformer. So, and the measured signals goes out of the tent here over the preamplifier. So you have on the other side of the cable here the PNC connector. So this is our measuring cable, goes through the amplifier and then out of the box. Here you can see now the outside of the shielded tent here. Here you can see the different connectors which are inside the reference plane. What we need for these measurements, of course, we need here for doing these measurements a spectrum analyzer, or we use here a spectrum analyzer. You can also use, of course, a test receiver or an oscilloscope with an internal FFT. For the connectors here, you see the AC power supply, you see here the Ethernet or RJ45, USB, and then we have here our 12-volt power supply for the internal preamplifier. And this is something what we definitely need, and there you have in the ESA1 set, you have this power supply cable. And to power the internal preamplifier, you have to plug in here this cable. Then we used for the preamplifier, for the measuring signal, we used the BNC connector, and this BNC output here you have to connect to the input of the spectrum analyzer or test receiver, and for this we use here the BNC cable. One side to the reference plane or to the BNC connector and the reference plane, the other side. I connect here to the input of the spectrum analyzer. Then to power the device under test, we used here one of the DC power supplies. If I open it a little bit, you see here internally I connected my power supply to the connectors 1. And of course now we have to provide here the power supply for our device under test, and for that we need there some external supply, and here with some cables I power my device. Now I want to show you the test setup with our device under test inside this tent here. For this we need some spacer here that we do not or that the electronic device or our measured device here is not too close to our reference plane. Now this is here our tested device, electronic with microcontroller and so on. And here you can see for the power supply of this electronic device, I prepared here a short cable with a connector for our RF current transformer. And here now we have the possibility to connect this power supply cable to our RF current transformer. And here I used the common mode connection for RF common modes, because I want to measure this device, or this device has a problem in the higher frequency range. And for radiated emission, the most of the RF currents are coupling into the cables as a common mode current. This cable here must be as short as possible because of the resonance which is created by the electronic or by the parasitic capacitance of the electronic to the reference plane, and the inductance here of our connection to the RF current transformer. And later we will see that exactly this resonance here we will see in our measuring results. If you need some other cables, for example communication cables like Ethernet or USB to run the device, then you can also connect these cables to the device here and then leave it to the outside here, or go to the outside over our connections in the reference plane. To show you now the measuring results, to make the setup easy here, I remove this Ethernet cable again, because we don't need it here for running the device. Now you can see here our spectrum analyzer, which is connected via the RF cable to the RF current transformer inside the shielding tent. And you see here in the spectrum, in the range from several kilohertz up to 500 megahertz, you see there a lot of disturbances coming from the environment because the tent is not closed. You see here that the device on the test is not powered, so these disturbances coming definitely from the environment. And if I close now the tent, then you see that all these disturbances are gone. And now I power on my device, and now you see the emission or the disturbances coming from the device under test. You see now here the result of the measurement, and what you can see here, this is the switching frequency of an internal DC-DC converter. And this resonance here at 150 megahertz comes from the internal resonance of the setup, because of the distance of the device under test to the reference plane and the inductance of the power supply cables to the RF current transformer. Exactly this creates this resonance frequency here. And you can see now, if I change the distance and the parasitic capacitance, so I bring now the electronic closer to the reference plane and close the tent again. Now you can see here that this resonant is shifted down to 100 MHz. I put the trace before here in the memory trace, that you can see the older curve in green and the new one in yellow. Now for the next measurement, we go back to our higher isolation here. That you place it again back to the isolated foam. And now we want to find out where we have some problems on the PCB here. Because we find out that in these measurements here or in the antenna measurements, we know that we have a problem in a specific frequency range. And now we can use some near field probes, for example here E-field probe, to check if you can find the same or similar frequencies or disturbances also on your PCB. And there you always start with bigger probes here, so that you, for example, can measure with this RFE02 probe, that you measure in a bigger distance above the surface of the electronic. You cannot go extremely close to the components, this makes no sense. Here with these bigger probes, you measure in a bigger distance above the electronic. And the same you can do also with the magnetic field probe. Here I use a bigger magnetic field probe. With this probe you can go along the edge of the board to measure the magnetic fields coupling around the PCB on this side or on this side. You can measure on cables here. Or also when you have here a connector, a board-to-board connector between this PCB and this PCB, there you can measure the RF currents which are coupling over this connector here. And if you see that there is a problem, then you use some smaller probes. This is then a smaller magnetic field probe. And then you can go deeper into your layout or deeper in the PCB. Because with the smaller probes you have a better resolution, and then you can find the traces or the pins here in the connector which are creating these disturbances. Now if you want to simulate that some other cables are connected to your electronic, you can use here this RF bypass for simulating some additional cables. Here you can see that inside this RF bypass you have different capacitance, and now you can use there a short cable to connect one of these capacitors. For example, I choose here 100 picofarad and then connect it to your electronic or to the connector of the electronic. And now you simulate here a cable which is connected over a parasitic capacitance of 100 picofarad to the environment, to the reference plane here. Here I want to show you now another measuring setup. Now we want to measure how many disturbance is created by this connector here or from this front panel board, which is here connected to our main board. And for this measurement we have to change something. So now the RF current transformer, we put it not into the power supply of the complete board. Now we use a cable and connect our power supply directly here to the inputs. So now for this measurement, we have to connect our ground of the main PCB with our reference plane, so that between this plate or this plane here, this PCB, and our plane, we got no more voltage differences for our measurement. And for that, we use some copper tape. And I have here these holes in the PCB, which are connected to the internal ground. And now I use this copper tape here to create a connection to the reference plate. And this I do also here on the other side, so that I have a very good and low impedance connection to the reference plane. Now I have to connect our RF current transformer to the ground of the front PCB. For this I have here such a small connector. This I bring here also in the common mode input. And now I use also one of these cables here to connect it to the ground of the front board, of the front panel board. And now we measure only the voltage difference which is created between these two ports here. And so you can evaluate if your problem is created by the main PCB or if the problem is created by this connector or by the front PCB. You have also the option, if you have, for example, shielded cable like this one, which is connected to the device under test, you can also connect the RF current transformer directly to the shielding. Here I removed the isolation of the shielding, and then you connect the current transformer to the shielding here. And because of that, this ground here of the main PCB is connected to the reference plane, then we measure only this part here. And if this this shielded connector is creating some voltage difference between the electronic and the cable itself, then we measure it with the current transformer here. If you would like to save your measurements from the spectrum analyzer for reporting or for documentation, you have the possibility to connect your spectrum analyzer with your laptop or with your computer. And then the ESA1 system comes with the software called ChipScan ESA. And this is what I would like to show you now here. And after the installation of the software, you can start it by clicking here of this icon. And then you see here the software ChipScan ESA in version 5. Here you see the toolbar with different settings. You see on the right side the settings for the spectrum analyzer. And you can see here the trace manager. For connecting an external device, you have to open in the toolbar here under Devices, the Device Manager. In the Device Manager, you can see that you have different possibilities to scan for the spectrum analyzers. You can choose between a serial connection, between GBIB, or an Ethernet connection. Here we have chosen the LAN connection with an automatic IP search. If you know the IP address, you can go to the manual IP and type the address here in. We use automatic IP search. If you know what type of spectrum analyzer you have, you can choose it here. Or if not, then press detect device, and then you can see here the identified devices. Here I found now the spectrum analyzer from Rohde and Schwarz FPC 1000. You can also delete it if you look for a new one. If you have different one, then you will find it here in this list, and you choose the one with that what you would like to work. Then you can close this window again. Now I want to show you how you can change the settings of the spectrum analyzer. For that, you can use here the spectrum analyzer manager. And at first, I change here in the toolbars under settings, I change the frequency to stop frequency. This is an easier way for me to set a start and stop frequency. Here I'm choosing, let's say, 1 megahertz. The reference level for the input you can change here to 70 dB microvolts. The attenuator, the internal attenuator, I change to 0 dB, and the ratio and BTU bandwidth you can also change to a different level. And in mode, you can change between continuous mode, single mode, average, max or min hold mode. And then press Z. So, and now the spectrum analyzer is set. You can see now in the live stream, when you press here live trace, then you can see now the live trace from the spectrum analyzer. Here under view, and at first choose fixed zoom, so that the Y axis here is fixed and this is not changing anymore. So now you see here the live stream or the live spectrum from your spectrum analyzer. Now it is also possible that you only take these measurements here under or with the button take. Then you can take in this measurement to your computer, and then you can see these measurements in the trace manager. Here under the trace manager you can give there annotation for your measurement. Let's say this is measurement number 1 and this is our normal mode, for example. You can give some comments here, for example, what is the modification without modification, let's say. And also you can give there another color. If you say, okay, this is my first measurement, and then give it to the red color. And here the trace manager, you can now switch off and on these measurements here. So, of course, you have also the possibility to zoom in the spectrum, zoom out. You can go wherever you want to go. And with zoom all, you go back to the complete frequency range here. After a modification, for example, when you change something in your device, then you get a new trace here, take a new one, and then you can see, okay, what is changing to your first measuring result. Then you say, for example, this is my second measurement, modification 1, and then insert 100 nanofarad. So, for example, then give it another color, and then you can see you can switch it on and off, can compare these measurements. You can go to the detail, can say, okay, what's the frequency range of this? For example, here this resonance is located at 140 megahertz. This resonance here is at around about 100 megahertz. And with these marker points here, you can go through these measurements and see, okay, what are the specific frequencies if you have there, or if you see there some harmonics or some other frequencies of your device. Here in the Trace Manager, you see here under the tab Traces, your measurements. Under Corrections, you see here some different correction curves. For example, the most of the correction curves here inside are from the equipment of the Langer EMV Technik, but you can also implement here some correction curves for antenna, for cable attenuation, for different other systems. And under limit lines here, you can create here your limit lines for your standard testings or for your pre-compliance testing, wherever you need some limit lines. And these limit lines you can also switch on and off then for the diagram here. On the right side of the Trace Manager, you have different or some other functionalities here. You can, for example, do some calculations with your measurements. You can see what the min and max levels. You can merge your curves. You can smooth it, whatever. You can import, export some curves here and create a new one, or duplicate some of these curves here. I will show you, for example, some adding or the adding of two curves. I select both curves, go to add and say, okay, I want to sum up all traces in the linear grid, and then say okay. And then I have here the curves, which is the calculation of both measurements together. Also on the right side here, under Spectrum Analyzer, you can, if your Spectrum Analyzer has a tracking generator, you can select here the properties or the settings for the tracking generator. Here under Corrections, you can select one of the corrections, what you find also in the Trace Manager under Corrections, and can choose one of these corrections so that your measurements will calculate it with this correction. And then you have here for the live trace, this is what I've shown you already. Zoom all, you see the live trace here, you can switch it on or off. You can take a hot copy from your device. You take is the button what you need to measure your curves from the Spectrum Analyzer, or you do a complete measurement here with the measuring button. Also a good tool is, for example, if you want to know where these harmonics or this disturbance come from, and you have not a real idea if this is a harmonic of some frequencies on your PCB, then you can do it in that way that I will show you here with, let's say, measure up to 30 megahertz. That. Then we decrease a little bit here. So, and then live trace, and then we go to the X ranges and measure, or want to see the X ranges up to 30 megahertz. Set. Okay. So, and now you see here some harmonics, and of course now it is easy to see, okay, this is here a harmonic from 4 megahertz to 5 megahertz, 6, and so on. This is the harmonic of 1 megahertz. But you can also show it under the toolbar View Harmonics, and then show the harmonics of exact 1 megahertz. And can give it, can choose another color here, for example. So, and then you see here that you see the different harmonics from 1 megahertz. And you see also in the higher frequency ranges that you have, or that you see exactly these harmonics here on these lines, and then you know, okay, this must be a harmonic of your fundamental term of, in this case here, of 1 megahertz.